Welcome to topic 5, which is all about circuits. This is a fun topic because we get to learn some things which have some really interesting applications. Now, we're going to rely on information that we learned last year in our physics class, so I'm going to move quickly through some of the initial information. The first thing we're going to look at is electric potential difference, and this is the equation that we learned last year. Electric potential difference is the change in potential energy per charge, right, as a charge is moved between 2 points. So if you take an electron and you move it from one electron toward a proton, its potential energy will change. And if you take that potential, the change in potential energy, and you divide by the charge of the electron, you get the potential difference for the electron in moving between those 2 points. Here's the official definition, which we must be able to recite for IB. And instead of defining it in terms of potential energy, IB defines it in terms of work. So when you take that electron and you move it from one place to another, point A to point B, you do work on it. And they say that the electric potential difference is defined as the work, there's two thes in here, scratch out one, the work done between, per unit charge, right, work per charge, because it's energy per charge, to move the positive test charge, some random positive test charge, between point A and point B. And the equation, now, so that's the definition that you must be able to recite. This is the equation that we use for understanding the concept and even in solving problems, right? So in the equation, V is the potential difference between point A and B, and it's measured in volts, and it can be positive or negative. Sometimes we also call V we have a lot of terms. We call it the voltage, just the voltage, because it's measured in volts. And then when we're talking about the potential difference from one end of a conductor or a resistor to the other end of the resistor, we call it the voltage drop. So this has two other names, the voltage and the voltage drop, that we'll see. Delta PE, yes, and the unit is the volt. Delta PE is the change in electric potential energy. Its unit is joule, and we can make it can be positive or negative depending on if energy is gained or lost. Q, of course, is the charge. We measure it in coulombs, and it can be positive or negative. Positive charge is carried by protons, negative charge is carried by electrons. So if you look at this equation, and I want you to write this down somewhere, the volt, right, is equal to the joule divided by the coulomb, the joule divided by the coulomb. 1 volt is equal to 1 joule per coulomb. Okay, so write that down somewhere. And don't get confused, this V stands for potential difference, and this one over here stands for volt. Last year, we gave potential difference we called it delta V. This year, we just call it V. We leave off the delta. Now, as it turns out, joules, our unit for energy, is way too big to describe the energy that electrons have, or protons. So instead of using the unit of a joule, we use a different unit when we're describing the energy possessed by electrons and protons. So the energy we use, the unit that we use is the electron volt. And the electron volt is defined as the amount of potential energy that an electron gains as it moves across a potential difference of 1 volt. So if you look back at this equation, plug in the charge of an electron, and we're going to move it across 1 volt of potential difference. So plug in 1.6 times 10 to the negative 19 coulombs. And then over here for V, plug in for V 1 volt. And if you calculate the amount of energy that the electron gains, it comes to this value, 1.6 times 10 to the negative 19 joules. And this is the unit that we use a lot of times. Now for practice, 21 joules isn't so big, we might think, but go ahead and convert 21 joules of energy into electron volts, and you'll see how huge it really is in terms of the units of energy possessed by electrons. Go ahead and solve this problem. You can read it. One thing to note, these values, 2 volts and 5 volts, neither of them is the potential difference, V. Right? Each of them individually is simply the potential. And to get the potential difference, you have to subtract one from the other. So do this problem as well. Electric current is given the variable I, the symbol I, and it's defined as the rate of flow of electrical charge through a cross-sectional area. So here's our defining equation. Current is equal to the amount of charge passing through some cross-sectional area divided by the time it took for that amount of charge to pass through. So here's the idea. If you were to take a long wire and cut it in half, right down the middle, and straight right down the middle vertically, and then if you were to pick up one end that you've just cut, and if you were just to watch and then count how many electrons pass through that end, that cross-sectional surface, if you counted the number of electrons, and let's say you counted over 5 seconds, if you took the number of electrons and multiplied by the charge per electron, that would be delta Q. It'd be the amount of charge in coulombs passing through that cross-sectional area, and then you would divide it by delta T, which would be 5 seconds in the example I made up, and that gives you the current. So what I've done in giving you this example is I've introduced the idea that cross-sectional area, really what we mean is the cross-section of a wire. So you could say that current is the rate of flow of electrical charge through a wire, if you wanted. Now current is measured in amperes, A-M-P-E-R-E, write that down somewhere. And charge is measured in coulombs, time is measured in seconds. So if you look at the equation, write this down as well. The unit of current, the ampere, is equal to the unit of charge, the coulomb, divided by the unit of time, the second. So write down that an ampere equals 1 coulomb per second. And all of these quantities are scalar. And look at this, they're all positive. That might sound curious, right? After all, in the example I showed you, I said count how many electrons pass through and multiply it by the charge in an electron. That would give you a negative charge and a negative current, not positive. So in physics, here's what we do. We don't deal with negative charges, we deal with positive charges. And when we deal with the positive charge, we give it this fancy name called conventional current. And it's really just the positive current, which would equal the negative current that actually exists. So we realize in physics, that negative charges are what flow. Those are charge carriers, is electrons. But even though electrons flow, we say that there are these positive holes which flow in the opposite direction as electrons, and that's what we use as our charge, right? The positive holes. Now, this whole business of holes, positive holes, yes, pun. This business of holes is a little confusing, so just think of it like this. When we're dealing with current, we make it always positive just by convention to make the calculations easier. And that means that we have to deal with some positive charge carrier. So just imagine that there's this positive charge carrier which is responsible for bringing the current through a wire. Okay. Electrical resistance is defined as the ratio of potential difference across a conductor to the current in the conductor. Okay. In other words, electrical resistance, R, given R, that's its variable, R equals V divided by I. That's our definition. You might wonder, why haven't I written it down? Well, we're going to see the equation again later. But you can write that definition down in your notes if you'd like. Now, what does it actually mean conceptually, resistance? Well, it's a measure of how easily charges flow through a material. So think of it like this. The higher the resistance, the harder it is for charge to flow. That means that if a material has a high resistance, it'll block charges more. And if it's blocking the charges, that means if you connect a conductor or a resistor, if you connect the resistor with high resistance to some battery, it won't draw a very big current because it resists current. If you connect a different resistor with a lower resistance to that same battery, it'll draw a bigger current because there's not so much resistance to the current presented by the resistor. Now there's another equation we can use for finding the resistance. As it turns out, resistance, R, is proportional to the length of the wire L and it's inversely proportional to the area, A, and the constant of proportionality is rho, the resistivity of the material, right? And when we're dealing with these kinds of things, we're always talking about either a wire or a conductor, or synonymous with conductor is resistor. So in this unit, resistor and conductor mean the same thing, okay? And that's what we're talking about, is the length of it. You know, if you were to lay it out flat, how long is it? If you were to cut it in half, right down the middle, and then look at the face that now is showing, the face of the conductor which is now showing, how big is that cross-section, that area, right? And the units for resistivity are ohms times a meter. Right? The unit for length of wire is obviously in meters. The unit for cross-sectional area is meters squared. And the unit of resistance is the ohm. Omega is the symbol we use for resistance, the unit of resistance, the ohm. And all of these values are positive. They are all scalars. Now, because the resistance R is inversely proportional to the area, that means that it's proportional to 1 over the radius squared. And it's also, we could also say similarly, it's proportional to 1 over the diameter squared, right? So there are problems we can solve where we say if you double, you know, the diameter of the wire, what happens, to the resistance of the wire? It's, of course, assuming that everything else stays the same. So go ahead and solve that. The way you do is you use this equation. You see that R times D squared, if you were to bring this over to the left, R times D squared is a constant because it's proportional to 1. So R1 times D1 squared equals R2 times D2 squared. And then plug in values that replicate the scenario. You know, double the diameter. Make D1 3 and make D2 6 so that it's doubled. And then solve for R2 and see how it compares to R1. And then go ahead and give this problem a shot too. We'll look at one like that in class. So remember before when I didn't write down the definition of resistance? Well, that's because it's the same as Ohm's Law. So here's Ohm's Law. It says that the current through a conductor or resistor is proportional to the voltage across the conductor or resistor over a wide range of applied voltages, now, provided that the physical conditions like temperature remain the same. Okay? A couple of things. The voltage across a conductor is synonymous with the potential difference across the conductor. And of course, I've said already, conductor and resistor, those are synonyms. So here's what Ohm's Law says. It says that V is proportional to I, right? Which means that they are related by a constant. So if you were to work out the units, you would see that the constant has units of ohms, and in fact, the constant is resistance, R. So Ohm's Law, right, it says that, well, if these things are proportional, then the constant of proportionality, R, is a constant. Excuse me. It's a constant. It doesn't change. So no matter what you do to the voltage, if you change the voltage, I will adjust in order to produce the same resistance in the material. Right? That's Ohm's Law. And be able to recite this verbatim from memory for the IB physics test. Now, we already know that I is the current through the conductor, V is the voltage across the conductor. You could also say V is the potential difference across the conductor, and R is the resistance of the conductor. So R is measured in ohms, voltage is measured in volts, and current is measured in amps. They're all positive, and from this equation now, you can see that 1 ohm, right, the unit of R, the ohm, is equal to the unit of V, the volt, divided by the unit of I, the amp. So go ahead and write that out. 1 ohm equals 1 volt per amp. Now, the thing about conductors is that they're not all ohmic. They don't all follow Ohm's Law. Some are what we call non-ohmic. So we use an IV graph, current versus potential difference, to show how different conductors behave and to compare different conductors. Of course, the slope of an IV graph, y quantity over x, it works out to be 1 over resistance.